Now that we've seen an example of how to kind of complexify our forcing function, if it's a sine or a cosine, we're going to take a look at another example. This time, not only do we have a harmonic oscillator, but it's a forced oscillator with a cosine function, and we also have some initial conditions. So we should not only be able to find the general solution, but using our initial conditions, we should be able to find the specific solution as well. And then, of course, it says verify the solution using Maple, which I will do in the Maple document that goes along with these notes that you have access to. So we're going to follow kind of the same process as before. And our first step, as always, is going to be to find our homogeneous portion of the solution, right? And so that means taking a look at the left-hand side of our differential equation and pretending that it was equal to 0 and not equal to -4 cosine 3t. So if that was the case, then we would be able to say our homogeneous differential equation would have a characteristic polynomial that looks like this: s squared plus 6s plus 8 equals 0. And this, thankfully for us, simplifies nicely. We have s plus 2 and s plus 4, which means we have two s values, -2 and s equals -4. And both of those lead to individual particular solutions, which we can combine to get our overall homogeneous general solution, k1 e to the minus 2t plus k2 e to the minus 4t. And so at this point right here, we've done the hard work of finding the natural state solution. So if the harmonic oscillator were left to its own devices, this would describe how that harmonic oscillator moves. But because we have a forcing function, that means it's a little bit more complicated. So our next step is going to be to find that particular solution. And we're going to do it this time not with a complicated sine plus cosine guess. We're going to do it by taking a look at our forcing function and complexifying our situation. And so we know that our forcing function, in this case, is cosine. So that means when we complexify, we only care about the real, this time, part of, and the real part of our guess, which is going to be a complex guess. Y sub c is going to be equal to some constant, alpha, times e to the I, and then you'll notice because our function up here is 3t on the inside of the cosine, we're going to make this I times 3t upstairs there, right? Which means that our first derivative of our complex guess is going to be 3i alpha e to the 3it. I'm going to change the order around a little bit. And our second derivative of our complex guess is equal to, when we bring that 3i down, it gives us -9. So it's going to be -9 alpha e to the 3it. So we have our guess, its first derivative and its second derivative, that we can now substitute into our original differential equation to see what happens. So I'm going to say we're going to sub these into the complexified dE. And complexified meaning we're going to not use cosine here. We're going to use the equivalent of that thing, that forcing function, but in complexified form. So it's going to look something like this. Since we have our guess, I'll continue with my color coding here. Second derivative is -9 alpha e to the 3it. Got to switch my colors back and forth here. Plus, our equation says 6 times the first derivative, which is this guy here, so 3I alpha times e to the 3it, plus 8 times our original guess, which is alpha e to the 3it. And then the right-hand side of our equation, we're not going to say it's negative 4 times the cosine of 3t. We're going to say it's negative 4 times e to the 3it. Now you might say, well, wait a minute, that's everything. That's both the real and the imaginary. You're right, but we only care about the real part. So I'm going to just put a little reminder so I don't forget. We only care about the real part. And so we'll be back. We're going to turn it back in a little bit, but for right now, we're going to play this out and see what alpha is going to be equivalent to. So simplifying things, recognizing that we can do a little kind of fancy footwork here with the e 3it. Each one of those we would be able to divide out, and those just become 1. And so that means we're left with negative 9 alpha plus 18I alpha plus 8 alpha must equal, on this side it's now negative 4. So we have the ability to solve for alpha once again. So it's going to be, with combining those two things, we have negative alpha plus 18I alpha equals negative 4. Let me scoot this up a little. With a little bit of fancy footwork, you can see we wind up with alpha equals, I'm going to factor out an alpha from this and then divide it over. It's going to be negative 4 on top, and on the bottom it's going to be negative 1 plus 18I. Right. And of course, that's all well and good, but it doesn't really make sense as a number because complex numbers can't be written like a quotient. So we have to use our rationalization technique, multiply this thing top and bottom by the conjugate. So it's going to be negative 1 minus 18I. And when I do that, the top gets a little bit more complicated. So we have positive 4 plus 4 times 18 is 72. So 72I. And in the bottom, we have, remember when we multiply our complex conjugates, we just multiply the lead terms and then the end terms. So negative 1 times negative 1 is negative 1 times negative 1 is positive 1. And then we have 18I times negative 18I gives me 326. And it's going to be plus because we have the I squared times the negative. So the entire number winds up being 4 plus 72I on the top, and the bottom just winds up being 320. Did I do 326? 8 times 8. 8 times 8 is 324. Did I do that right? Yeah, there we go, 324. So the bottom is 325 after we add the 1. Which we can rewrite as 4 over 325 plus 72 over 325 times I. So that is the alpha value, the complex number alpha value, that will actually produce a true, correct guess that will work as a solution for our complexified differential equation. So now that I have that, that means that I can write my particular solution. So down here, I'm going to go back to the purple here and say, this means that my particular solution is going to be that alpha value times e to the 3it. And of course, that's terrific and all, but we really want to be able to produce something that has a real and an imaginary part, so we're going to have to expand this. So if I scoot this thing down a little bit, my particular solution is all that stuff times, and that's basically the same stuff here, times e to the 3it expanded is going to be cosine 3t plus I times sine 3t. And so when I multiply this binomial times that binomial, I'm going to have a real part and an imaginary part. But again, we only care about the real part. So the real part is going to come from, we only want the real part. And the real part is going to come from this guy times this guy, but also from this guy times this guy. So there's going to be two terms that are real. And so you'll wind up with the real part is going to be 4 over 325 times the cosine of 3t. And this guy right here times that's going to give me a negative 1 from the I squared. So plus, sorry, not plus, I just got done saying it's negative, minus 72 over 325 times sine of 3t. That's the real part. Those two pieces are the real part. So this is the particular solution that I'm interested in, right? So now I have, if you notice at the top, I have my homogeneous part of the solution, and after my complexification, which seems like it's an awful lot of work, but if you tried to do that with a sine plus cosine guess, it had taken you at least as much work, if not more. I now have my also particular solution guess, and so the last step in the normal process would be to combine to get my general solution. And so combining these two parts, I have my general solution, which looks like this, k1 e to the minus 2t plus k2 e to the minus 4t plus two more terms, 4 over 325 times cosine 3t minus 72 over 325 times the sine of 3t. That is the general solution. And since I know I'm going to wind up having to make or make use of some initial conditions, we go up here and notice that the initial conditions are that the initial position, but also the initial velocity is equal to 0. So y prime, I don't actually have y prime, but I can get to it. Because if I know that y of t is equal to all this stuff, then pretty easily I can find out that y prime of t is equal to negative 2 k1 e to the minus 2t minus 4 k2 e to the minus 4t. I'm just taking the derivative. And then bring the 3 out front and make that a negative, so this becomes negative 12 over 325 times sine 3t. And then sine becomes cosine, and then the 3 comes out front. Minus 72 times 3 is 216 over 325 times cosine 3t. So I have both y and y prime. But notice, that is the general solution right there. But I need this to use my initial condition. Right? So I don't have enough room on this page, but I'm going to change over to the top of the next page in order to continue this problem. And so the very last kind of part to this problem is I need to solve. I'll leave that paper nearby so I can refer to it. I need to be able to solve for the particular solution using the initial conditions. And so in order to do that, I'm going to use what I knew for my initial conditions, which were that y of 0 was equal to 0. And that means from my equation, let's see if I can remind us here, this equation right here, if t equals 0, then these just become 1s. Cosine becomes 1, and the sine goes away. So I've only got these first 3 terms. It's k1 plus k2 plus 4 over 325. All right. And the other thing that I know is that if the y prime of 0 equals 0, then looking at my derivative function, I can say, oh, this will just become negative 2k1 minus 4k2. This term goes away now because it's sine. Sine of 0 is 0. And then I'm left with minus 216 over 325. So I'll have minus 2k1 minus 4k2 minus 216 over 325. So I have two equations that I need to be able to solve for my two constants, k1 and k2. And you can do this either by hand, or if you want to hop into Maple, you can type those two equations into Maple really quickly, which is what I'm doing. I did that, and I came up with k1 is equal to 4/13, and k2 is equal to negative 8/25. So I used Maple and solved my system. Okay, so what does it mean? Well, we just found our constant values for our general solution, which means now everything's all said and done, we can say our particular solution is going to be k1, which is 4/13, times e to the minus 2t, minus 8/25, k2, e to the negative 4t, plus our last two terms, if you remember, were 4 over 325 times the cosine of 3t, minus 72 over 325 times the sine of 3t. So it's a long bit of equation there, but that really is the particular solution given our initial conditions. And of course, you can always check it with Maple. And I strongly suggest that you do that. And you'll find out that those are exact values for those fractions. Now you might look at it and think, where the heck did that thing come from? Where the heck did, the 25 and the 8 and the 13 and the 325, how would you have guessed those things based on, if you remember, our initial equation? The only numbers involved were 6, 8, negative 4, and 3. And yet all these numbers, everything kind of comes from those initial parameters. So it just shows to go that you can't always just look at your initial differential equation and have an idea of where it's going, where you're going to wind up. So there's one more example to be done for this section, and it's basically more practice doing the same thing, but it's a slightly more complicated differential equation. So we'll leave that for the last video.